Hello everyone, and thanks for your interest in our paper. I'll be introducing our method for generating personalized locomotion patterns for lower limb exoskeletons using reinforcement learning. Different people have different walking patterns. In other words, step lengths, walking velocity, and range of motion for different joints varies from person to person. Even for one person, these features can be affected by aging or getting fatigued. Most of the commercially available exoskeletons use fixed and predefined trajectories for walking. Obviously, this will not be comfortable for all of the exoskeleton users. To solve this issue, we are introducing new approach to reshape exoskeleton walking pattern based on the physical interaction between robot and user. In our previous work, we introduced adaptable central pattern generators in order to modify exoskeleton walking pattern. This method receives physical human-robot interaction between human user and the exoskeleton and then translates that to new amplitude and frequency of walking. Amplitude represents the step length and frequency is the velocity of walking. The previously proposed adaptable central pattern generators was successful in adjusting walking velocity and step lengths based on the user's applied interaction. However, the effectiveness of this is limited to a precise initialization of the parameters. Also, if the parameter identification has been done for one person, it is not 100% guaranteed that it will work for different people. In order to resolve the previously mentioned problem, we have introduced a reinforcement learning-based intelligent central pattern generators. Despite the adaptable central pattern generator method, which was using the actual value of the physical human-robot interaction for tuning the gait parameters, the new intelligent CPGs use the effective energy which is being determined via reinforcement learning. In other words, the user's applied interaction force is being fed to the RL, and based on the interaction behavior that user shows over time, the RL agent amplify or decrease the interaction energy in order to reach the desired amplitude and frequency as soon as possible. As it can be inferred from the descriptions, having RL in the loop, the intelligent CPGs can modify gait pattern for each user independent of how the initialization have happened. But the question is how the reinforcement learning can adjust the physical human-robot interaction value. The answer for this question is the way that we design the reward function for this problem. The combination of the first two elements, which is difference between average and actual energy and average and actual frequency, and the RE element, encourage the system to reach the desired frequency with minimum interactions. The term with the second derivative of frequency encourages system for minimum fluctuations in the frequency. And finally, the RP forces the RL agent to always use safe range for both amplitude and frequency. So the combination of all of these terms encourage system to reach the desired frequency with minimum times of interaction. Let's take a look at some results. The CPG parameters has been initialized with a person who has a stronger muscle than the person wearing the exoskeleton. Here you can see the results for increasing the frequency. In the top figure, the dashed line shows the user's actual interaction and the solid line shows the interaction energy reinforcement learning has been suggested. In the down figure, you can see that the actual frequency, which is shown in the solid line, reached the desired value in about 25 seconds. The exact same scenario took 120 seconds without RL modification. These results are available on the paper. And for the case of decreasing the frequency, the user has reached the desired frequency in about 10 seconds. So without doing the exact parameter identification, only by using RL and letting that to modify the user's interaction energy, we can generate personalized trajectories in much faster way. At the end, I would like to appreciate all funding agencies for supporting this research and also appreciate you for listening to this presentation.